So today we are looking at capacitors. So capacitors are very common electrical components in things. Oh, this was, what was this? This is this is the inside of my TV. So you know how there used to be like the big like box TVs that were in all the rooms? When I took mine down, I went ahead and scavenged it because there's a cathode ray tube inside. You might remember from first year chem, we messed with cathode ray tubes, and those old TVs are cathode ray tubes. Inside here, there are several interesting things. There are transformers, not like Optimus Prime, but a transformer has a smaller number of turns on one side and a larger number of turns. It's like how many times the copper goes around. And so it transfers you from higher voltage to lower voltage, or from lower voltage to higher voltage, right? So you have transformers. The power lines go very, very, very high voltage and very, very, very low amperage because that gives you less resistance. So less energy is lost from the power plant to your house. So then there is a transformer in every neighborhood that takes it from very, very high voltage to a lower voltage that can go into a house, right? So then inside of things, a lot of times you have to do transformer stuff too. But what we're really looking at today is these capacitors. Here's a transformer that's visible, right? That's what I can't figure out where the camera is, even though it's in the middle of the computer. So this is a very small version of a capacitor. You see this blue thing, and then you have larger capacitors, and you can have some very large capacitors. A lot of them are smaller, about like this. So with a capacitor, I'll go ahead and break one of these guys off. This TV isn't going to work anymore anyway, so it's okay. I'm just snapping one off, right? So this guy just got broken off. And then I'm going to tear this apart. That's going to take me a second, so I'll pause this for a second. Okay, so that was about 7 hours. It was a couple minutes. So it's just got like a plastic coating on the outside, and then it's basically a metal thing. It looks kind of like a battery. It's got a prong coming in and a prong coming out and stuff. But I used some pliers and peeled off some of the top part. So now it just slides right out, and it's a little gray tube. I normally like to be able to pass these around to students and stuff so you can feel them. The gray tube it's not wet, but it's got like an oil substance on it. And if we slice this guy open, there's like kind of a tape thing on it. So this is one of those things we normally gather around in a group and kind of do this together and stuff. I really don't like this distance edge stuff. It's nowhere near as satisfying. So anyway, peeled the tape off. And this one is a little different. I haven't normally seen this. Oh, there we go. Peel that rubber off there. Rubber just is an insulator. And then if I can find it, here we go. So as I peel this part off, we now have gotten to some metal. And it just unrolls. Oh, I'm peeling off some more of it. See, there's the metal's got a couple layers of stuff here, right? So there's this layer, and then there's a metal layer, and then there's another layer of that kind of goopy stuff. It's a diode material. And then there's another layer of metal, right? So you see how there's 2 layers of metal, and then that coils all around itself. So as we're going through the notes, we'll kind of talk about there's 2 parallel plates. Well, these don't look parallel, but they were parallel because it was that insulating substance, metal, insulating substance, metal, insulating substance, right? So if we kind of, the green is the insulating substances and the purple is the metal, you do end up with 2 parallel metal plates. They're just wound around in a coil, so it doesn't take up a gigantic amount of space. Right, so it's just this real thin metal, and then it's got this insulating material that kind of is like an oil stuffed on it. So I'm going to wash my hands, and then we'll go through some notes. All right, so the quick notes to go along with the capacitors and stuff. Just a quick review here on stuff we've done so far, right? We have the idea of current, which is how much charge per unit time. I don't know that we've actually done any of these equations. That's not, basically how many electrons are passing per second. But there's an equation for that. This one we use a lot. Voltage equals current times resistance. That's Ohm's law in lots of different ways. We then introduced this week power. There's several different power equations, but the basic one is power equals current times voltage. Change in voltage is used, right? So for a light bulb, it's the voltage across the light bulb and that kind of stuff, right? So same idea as voltage, right? There's nothing weird with that or whatever, right? So we've done those things so far. We're going to add to those. Oh, yeah. And then in series and parallel, we've been messing with those a good bit, right? So the current is the same everywhere, whereas in parallel, you add up the currents to get your total current. The current in each individual path is going to be the same as the total current when we add them up. For the resistances, you add up all your resistances in series to get your total resistance or your equivalent resistance. And in parallel, it's inverses all over the place for that. Here, current is the same everywhere in series. And then we had already kind of talked about that in parallel, right? So hopefully we're continuing to, those are, making sense and all that kind of stuff as we're going through those. So for a capacitor, right, this is kind of how they draw those capacitors. And that is not easy to see. Let's change that background. I grabbed a new background color. Let's just go to a really light background. There, that's easier to read. Okay, so this is the parallel plate kind of thing, right? So you've got, you hook it up to an electrical source. You get, as you put it up to an electrical source, let's say follow the electrons instead of traditional current. Traditional current is positive flowing one way, when in actuality it's negative flowing the opposite. But we get all these electrons going this way, and you get this buildup of negative charge here. And as that happens, electrons have to pull off of this area to complete that circuit. So you hook it up, and it's like you go along, but then there's a gap, like a canyon, without a bridge between. So you've got this dielectric material, which is an insulating kind of material in between there. And the bigger your charge buildup here, the more energy you have. This is a lot like a battery in that you can use it to charge things, but it's held mechanically instead of chemically. Advantage to holding things mechanically is you can discharge it very quickly. Think a lightning bolt. A lightning bolt is a natural capacitor. It's got a big plate, a big pillow. I'm not an earth scientist. A big cloud thingy. I think it's a marshmallow that floats in the sky. I don't know. You've got this big cloud that floats in the sky that gets a negative charge on it, and then the ground gets a positive charge on it. And then if you get too much of a charge on it, it will disperse between those. Air is a dielectric. It's not a particularly strong dielectric. So you need a lot of space between them and stuff. But anyway, how much it can hold is a charge of kind of what's the distance between the plates, how big are your plates, all that kind of stuff is a charge there. So you saw on the capacitors I had, some of them were much larger, some of them were much smaller. They tried to put a dielectric in there that you could get the plates very close together so that they would still hold, they could hold a lot of charge in those. But you can do quite a bit with those. I'll show you something a student built here a couple of years ago. As one of our electrical projects. It's kind of sad that we don't get to do electrical projects with you all this year, but you can still play with stuff at home if you want. Right. So some equations. These are kind of our big equations. The capacitance is basically your size of your capacitor, right? How much can it hold? How big is your bucket? If you think about the charge being like the amount of water in the bucket, right? The capacitance is the size of the bucket. The larger C, the larger capacitor you have. There's a physical property of that capacitor. Q is the charge on the plate. So that's like the amount of water in the plate. And then V is the voltage. That's like how hard you pushed that water into the bucket, right? The harder you push the water into the bucket, the more water you can get in the bucket, right? So the harder I push, I could quit with that metaphor, right? So the harder I push into my capacitor, the more charge I can get on my capacitor. If I do too much, though, it can cause a problem. Oh shoot, I didn't bring a capacitor over with. Anyway, when we look at the side of capacitors, they will give us a capacitance rating on them. So if you look at this guy here, can we make out that 1F? See that 1F? That's 1 farad. This is a 1 farad capacitor. That's actually a pretty large capacitance. You don't really see 1 farad capacitors very often. It's the way this thing is made. And then the 5.5 volts means that you can't push stuff very hard onto this. That's why you're able to get as big as a 1 farad capacitor. Normally, capacitors say things like, this big one right here says 820 microfarads. So this large one is actually a smaller capacitor because of the way that it's designed. But you can push it up to 200 volts, right? So you can push a lot harder onto that one as opposed to this little guy. If you go over the voltage rated on these, they will burn through that dielectric. You'll actually smell it. I've had students have that happen when they were working on things. They'll burn through it, and then you smell that it's burned out, and then it just never works again because you've burned through that dielectric. So it's like there's a hole in the bottom of the bucket, so you can't hold any charge or whatever, right? So then another way we can calculate that is this E. This is permeability of the substance between the plates. There is an that's like air has a certain permeability. The dielectrics in these guys have a different permeability and that kind of stuff. That's like a constant for those. Area of the plates, and then the distance between the plates, right? So we have those. None of this math is all that hard, but we can calculate basically, how much charge we can hold with a different capacitor and all that kind of stuff, right? Then you can calculate how much energy is held in them with some different equations. This first one is the most obvious one. The higher the charge and the harder you push onto there, the more energy is stored in the capacitor. We're not going to do a lot of super crazy stuff with these, but we will work a few problems with each one of these so that we can kind of learn a little bit about capacitors, right? We will probably skip those until Monday. I don't know how much time we're already sitting at. But the basic idea on capacitors, what you can do with them, right? So you can load them up and then discharge a bunch of energy all at once. I've seen people who have taken the batteries out of their car and replaced them with large capacitors, multiple large capacitors. These are like electrical engineers, not like, Bob. And so you could do something like that. So you can discharge a bunch of energy at once. They also can be used to time things. So when you press a button and they want it to pause for like 2 seconds, then you basically, as the stream runs across, the water fills the bucket before it can go past there, right? So it's something along those lines. So you can use it to time things, like when you press the elevator button and it waits for a couple seconds to close the door. That's a capacitor filling. So when you get into some advanced physics classes, you can do a lot with those capacitors and that kind of stuff. We're basically going to calculate how big is your capacitor, how much charge is on it, how much energy is on it, just a few things like that. But that's basically what we're going to finish out the year with, is a few of those kinds of things.